Hi, my name is Arman Nikoshirazi. I'm from the University of Michigan. I'm going to give a talk on what I call the Heisenberg interpretation of quantum mechanics, which is a talk I was supposed to give on March 5th at the APS March meeting in Denver, which got canceled because of the coronavirus. So, in the mid-1950s, Werner Heisenberg gave a series of lectures and then put them into a book called Physics and Philosophy, The Revolution in Modern Science, in which he drew a distinction that was really inspired by the philosophy of Aristotle and which is well represented by the following quote. Heisenberg said, "In the experiments about atomic events, we have to do with things and facts, with phenomena that are just as real as any phenomena in daily life. But the atoms or the elementary particles themselves are not as real. They form a world of potentialities or possibilities rather than of things or facts." What is really striking to me is that Heisenberg, who was one of the founding fathers of quantum mechanics and a physicist, never went beyond turning this little piece of philosophy, this distinction between possibilities and potentialities versus things or facts, into a piece of physics. But I will attempt in this talk to present I will present an attempt to do that. So as a warm-up, I would like to first bring to consideration the case of classical probability. It turns out that there is a similar distinction, or a similar distinction can be argued to exist already in axiomatic probability theory. So to illustrate it, imagine the following example. Suppose I have a die and I haven't thrown it yet. So there is no outcome, but if it's a regular die with the numbers between 1 through 6, the outcomes still exist in some sense as possibilities or potentialities. And this can be mathematically modeled in terms of a fiber, an inverse projection. Now, the word potentiality is used in many different contexts, and for that reason it has a lot of baggage. I prefer to choose a term that doesn't have as much other connotations, and so it can be more closely associated with the distinctions that with the very specific distinctions that I'm talking about here in Heisenberg's sense. So I will call it an actualizability. So mathematically then, we can do the following. We can basically amend axiomatic probability with a little bit of extra structure that is meant to capture this idea that outcomes which haven't happened yet only exist as possibilities or potentialities. So what you see here is in the black color is a standard axiomatization of probability, and what is in red is some extra structure. So nothing was changed of what already exists, only a little bit of extra structure was added. Namely, a set, gamma, which I call the outcome set, and map, a function, which is a bijection, so it's a one-to-one correspondence between the sample space and the outcome set, and which puts basically one element of each set into correspondence with an element with the other, and an axiom which says that probability is a measure on a fiber on each element of the outcome set, such that this fiber is just what we call the sample set. Now, this is basically meant just to capture the concept of probability. And here's an interesting thought. Suppose that you wanted to actually define a non-probabilistic unit measure, like a unit length or a unit volume. How would you do this? Well, it's very simple. Just get rid of all the red stuff here. But notice what you get back is just the standard definition of probability, the standard axiomatization of probability. So it turns out that what everybody calls probability axiomatically is not really a probability. It's a non-probabilistic unit measure. And this gives rise to an interesting problem. I call this the equality of inequivalence problem. And I have a separate paper that just focuses on this particular problem, which is amended to the material here. I call the title of the paper is Heisenberg's Equality of Inequivalence Problem. But there is basically, this is the idea, that the way we tend to think of the distinction, intuitively at least, between possibilities or potentialities on the one side and things and facts on the other, is that the first category, you can have mutually incompatible possibilities that coexist, but you cannot have mutually incompatible facts coexisting. And so that makes them mutually exclusive. Also, we can think of physical systems as being basically covered, the description of physical systems being covered by either being described in terms of the physical systems described in terms of a fact or in terms of a possibility. And so these two together imply that facts and possibilities actually partitions a set. So when you have these two features that are mutually exclusive and they cover the entire set of descriptions, that implies that they partition the set of descriptions of physical systems. And that in turn implies that facts and possibilities are really equivalence classes. And so if the quantum, if in the case of quantum mechanics, this distinction between the quantum world and the classical world is based on this distinction between facts and possibilities, then it inherits that equivalence class structure. And now if you consider the standard quantum superposition equation, it can be interpreted in two possible ways. In both ways, the right side is always, if you're trying to incorporate this, seriously incorporate this distinction, the right side always has to represent possibilities. Why? Because you have mutually incompatible coexisting states. And by the distinctions that we made, that means it's a possibility. Now, the left side of this equation can be interpreted in one of two possible ways. It can be an unmeasured quantum state, but that's not a problem at all, because that is just what you mean also by a possibility. So both sides are possibilities of the equation. But another interpretation is possible, and that is that the left side represents a fact. And so on the left side of the equality, you have a fact. On the right side, you have a combination of possibilities. And we just said that facts and possibilities actually have an equivalence class structure. So you have an equality between two members of different equivalence classes. And that basically renders the entire distinction, the entire formalism, incoherent. So what this means, surprisingly, is that you cannot, not only does quantum mechanics not have any sort of distinction along the lines of what Heisenberg suggested, but when you try to seriously put it in, it breaks the theory, it breaks the formalism. So my attempt to address this problem is very similar to what I did in classical probability. In the axiomatization of probability, I proposed a little bit of extra structure to help capture the concept of probability, and so it is here. Essentially, it's basically some extra structure in the quantum formalism to basically implement the Heisenberg's distinction at the level of the quantum formalism. So there's again zeroth postulate, basically, which just establishes that Hilbert space is an actualizability space. So unlike in the case of probability is just basically, you can think of it as a theory in math. So you don't really need to be too concerned about making distinctions that have physical meaning. And this zeroth postulate here is really more along the lines of establishing a physical meaning, which I think in this case is legitimate because quantum mechanics is, after all, a theory in physics. Then we have the first postulate, which is just the next three postulates are just the standard textbook postulates, that a physical state of a quantum system is represented by an element of the Hilbert space, and that observables are represented by linear Hermitian operators acting on the elements of the Hilbert space, and that the time evolution is given by the Hamiltonian. So this is just the same as the standard formalism. Now, in the standard formalism, the next postulate would have been something along the lines that measurement leads to the reduction of the quantum state, and that postulate is now replaced by the following. It says that whatever it is that we call a measurement is represented by a map from the Hilbert space to another set, and this set is what I call the set of classical states, and the map will be called the actualization map. And the image of the map is a subset of the classical state collection, which is a collection of all basis states as actualities in the measurement basis. The classical state collection is a collection of all basis states in all possible bases. So that's the difference. It's in the subsets. The image of the map is just the collection of basis states in the measurement basis. And then in the textbook, the next postulate would normally be just the Born rule. And here it is also basically the Born rule with one small change, that what the Born rule refers to in the standard formalism is again an element in the Hilbert space, but now we don't have, if it's a member of the classical set, then it's not an element of the Hilbert space. So the Born rule, the referent of the Born rule is a little bit different, but the mechanics of it are exactly the same. And then we need one other postulate that is not found in the textbook version, which reconciles the fact that once you do a measurement on a quantum state, after a while the state spreads out in accordance with the Schrödinger evolution, and that is represented by another map that takes you back from the subset of the collection of classical states to the Hilbert space, such that it hits an eigenstate of the original quantum state, and that will be called the deactualization map. So it's really a very simple modification that I'm proposing here, not really mathematically sophisticated at all, but it turns out it delivers a lot of bang for the buck, or at least so I would argue. So here's a schematic to illustrate what's happening. What really the principal change is that this modified set of postulates that I call the Heisenberg interpretation introduces. In the standard, if you look on the left, in the standard textbook formulation, you just have state reduction. The quantum state upon a measurement is reduced to an eigenstate. Whereas in the Heisenberg interpretation, what you have is a composition of two maps. One map takes you from the Hilbert space to the outside. It takes you outside the Hilbert space to the classical set, to the classical states, and then as a other map, the deactualization map, takes you back from the classical states collection to the Hilbert space, such that the composition gives you back an eigenstate. So, even though this is a really simple modification, I would argue it has a number of advantages over the standard formalism. In the paper that accompanies this talk, I do discuss all of these in some detail. The paper is unfortunately not quite ready yet, but it is in advanced stages of completion at this time. I will only very briefly talk about 4 of these, the ones that are highlighted in blue here, what I see as advantages over basically the textbook formalism of standard of quantum mechanics. So first, the problem that I mentioned before, the equality of inequivalence problem, the Heisenberg interpretation basically resolves it completely. And the reason is that the quantum superposition equation can only refer to to elements in the Hilbert space. And remember, by the zeros axiom, those elements represent always actualizabilities. So you always have actualizabilities on both sides of the equation. You never run into this incoherence problem. And the actual state, or the thing or fact, which is a measured state, is represented by an element of the state of the classical sets collection. And because explicitly that one doesn't have a Hilbert space structure, you can never write it in terms of a combination of other states, like in quantum superposition. So the problem completely disappears. Second interesting consequence of this interpretation is that it circumvents the violation of unitary time evolution. This is a problem that has been recognized since von Neumann basically formalized quantum mechanics in the early 1930s, and he already recognized that there needed to be two different time evolutions, ways of state moving forward in time, which are incompatible with each other. But you have to recall, the incompatibility is only a problem if the two ways of evolving in time share a common domain of applicability. And that has been the unspoken assumption, as far as I can tell, all along for the last 80, 90 years. But what the Heisenberg interpretation does is it separates out their domains so that they become mutually exclusive. And basically it steps around the problem in that sense. So the elements of the Hilbert space always obeys the Schrödinger evolution. The element of the classical set does not obey the Schrödinger evolution because it's not that set is not a Hilbert space, and so the Schrödinger evolution does not apply. And then when you go back from the actualized states and deactualize back to the Hilbert space, the state obeys the Schrödinger evolution once again. So you never have this problem with the non-conservation of probability. What you have instead is basically that the Hilbert space, in the standard formalism, the Hilbert space at all times is part of the representation of a physical state. And what is different here is that's no longer the case. The Hilbert space is only part of the representation of a physical system as a actualizability, as a potentiality or possibility, not when it actually represents a thing or fact about the world. And one way to at least make this more plausible is that you could argue that classical probability has a very similar process going on. So imagine again my die example. When I haven't thrown the die yet, all the possible outcomes exist, are elements of the actualizability fiber, which is the sample space. Then when I throw the die, I get an outcome. This outcome is now a thing or fact, and it's not an element of the fiber, it's an element of the outcome set. And remember, probability is not a measure on that. Probability is not a measure on the outcome set. It's a measure on the sample space, which is a fiber on each element of the outcome set. So the probability does not apply to it. And this reflects the idea that this is just a thing or fact. It's not a possibility. And probability, intuitively or conceptually, we might think of as a measure over possibilities. And then you can imagine that I pick up the die once again and prepare it for a new throw, and in that process the fiber reappears again, and once again the outcomes are represented by elements of the fiber. One interesting thing is aspect of this interpretation is that it brings attention to novel symmetries. So the standard formalism of quantum mechanics has what I call ontic status symmetry. Now, this is the kind of thing that wouldn't be really even worth mentioning until another symmetry comes along that is incompatible with it. And now suddenly you need to actually have a name for it, name it, and point it out. And basically what it says, what untitled symmetry says, is that under the invariant of each, under the interchange of a physical system, it's untick status. So whether it's a potentiality or whatever, or thing or fact, it doesn't change. And this is directly a consequence of the fact that all physical systems are elements of the Hilbert space at all times in the Standard Formalism. Now, the Heisenberg interpretation breaks the symmetry because some physical systems are not elements of the Hilbert space, namely those that represent systems as things or facts. And so that symmetry is broken, and it is actually replaced by a different kind of symmetry, which I call the actualization symmetry. This is basically an invariance of what functions as a measurement device, and what functions as being measured, or in the language of this interpretation, what is doing the actualizing and what is being actualized. So the two interpretations are mutually incompatible, and in this table I try to point out basically some of the ways in which they are incompatible. So for example, in the Standard Formalism, we classify the entire measurement apparatus and the quantum system as having the same ontic status. And remember, this is enforced by the fact that you get, if you try to introduce a distinction, you run into the problem of the equality of inequivalence. Whereas in actualization system, actualization symmetry, you only have this between the quantum system and the microscopic constituent of it. And the actualization symmetry requires an ontic distinction. The ontic status symmetry doesn't. Measurement in the actualization symmetry must be an ontic transformation. So, in other words, going from a possibility or potentiality to a thing or fact, whereas explicitly, as I showed with the equality of inequivalence problems, you cannot have such a transformation. You cannot introduce it into the Standard Formalism without breaking it. And actualization symmetry is compatible with the actualization. Ontic status symmetry is not compatible with it, mainly because you can only have one kind of ontic state. And this also influences thinking in other respects. So, for example, decoherence, or whether it's possible to think of a wave function of the universe. I think one of the useful aspects of pointing out these differences, these different symmetries that underlie these different conceptions of quantum mechanics, is that they influence our thinking in other areas that may not immediately seem connected to it. So I've heard, for example, some physicists say, yeah, it's perfectly obvious that there has to be a wave function for the universe, and other physicists who have said that it doesn't at all make sense to them what that even means. And I think the reason for this this great difference in conceptions, I think, is that in the background there may be some other assumptions that the physicists have about the world that influence how much sense they can make out of it, or how plausible it seems to them. And so pointing out to these symmetries can help prevent instances where people talk past each other. And then finally, the Heisenberg interpretation sets the stage for new experimental predictions. I'm very careful in choosing my words. I say setting the stage for a prediction versus making a prediction, because for the predictions inside quantum mechanics, there should really be no difference. But where there is a difference is how quantum, or there potentially, or where it sets the stage for there being a difference, is how quantum mechanics relates to gravity. But how it relates to gravity needs to still be made explicit or defined by an external assumption, because the Heisenberg interpretation says nothing about gravity. So the simplest assumption about how this relates to gravity would be just to say that classical means subject to general relativity. So you just identify the two. And if you go with that assumption, that's probably not the only possible assumption, but it's the simplest and most natural, I would argue. When you introduce it, when you make this assumption, it introduces a sharp boundary between general relativity and the standard model that was not evident before. And so, and the existence of this boundary is what leads to new predictions. So the new predictions are not within the domain of quantum mechanics or within the domain of general relativity, but how they relate to each other. So one possible prediction is that each quantum measurement, if really the correct way of thinking about it is it involves the transformation of some possibilities into turning some possibilities or potentialities transforming into thing or fact, and that thing or fact is now in the domain of general relativity, then that immediately implies that each measurement creates a tiny gravitational field. Now this is probably not measurable. If you probably are years, decades, maybe centuries, or perhaps forever away from measuring the gravity fields of atomic-sized systems. But there is another prediction that is actually feasible, I believe, with today's technology, even though it wouldn't be cheap. And the prediction would be that light, which is inherently a quantum phenomenon, would not be a gravitational field source. Now, under the current worldview, it is perfectly obvious that light must be a gravitational field source. There's no way it could be otherwise. One standard argument is, well, we have plenty of evidence or plenty of examples of gravity bending light. And so by a conservation of momentum argument, we can say that, well, if gravity acts on light, then light has to act back. And that would mean that light has a gravitational field. But this argument cannot apply in this case, because if light really is a potentiality, then it is not the kind of thing that can be acted on or that acts back on actual physical systems. So really the way to think of it would be basically potentialities are just constrained by the circumstances, the arrangement of the actual things or facts. In this case, this is the background space-time, the curvature of the background space-time, and so that just constrains how the potentialities can manifest themselves. Quantitatively, this would be done via how the path integral changes in the against a curved space-time. So conceptually simple test, but technologically probably not so simple, would be to try to measure the gravity field of an ultra-high energy density laser beam. And the prediction is very straightforward. If light really is a potentiality, we should get a null result. Now, in my opinion, this is one of the best possible big experiments that could be done in fundamental physics. Compare this to large particle accelerators. There are discussions to build the next generation particle accelerator larger than the LHC at the cost of maybe $20-30 billion, but it's very risky because we don't have reasons from within established physics to assume that it will find anything. We have reasons from speculations, but the speculations are just that. They're not established. So the situation is very different from, let's say, the discovery of the Higgs boson, which was basically predicted by established theory. We don't have something analogous right now. And if all that money is invested and the accelerator doesn't find anything, then it would probably substantially damage fundamental physics research. But in this case, in this trying to test whether there is a gravitational field for ultra high energy density laser beam, you would not face this risk, because either way it would be a success. If the field is found in accordance with what we expect, then the Heisenberg interpretation is false, and but it's the first definitive piece of evidence that gravity must in fact be quantized. And this would reflect the largely unspoken assumption that currently that gravity and quantum, the standard model, share a common domain, which is what the Heisenberg interpretation exactly separates out. And if a null result is obtained, then the current paradigm will change. So either way it goes, this experiment would be a success. So I introduced the Heisenberg interpretation of quantum mechanics. I went much more leisurely than I would have in the actual talk, so that's why it took 3 times longer. I tried to list a number of advantages. There is a paper that comes with it. I will try to get the paper out as soon as I can. If the interpretation captures the distinctions, the reality correctly, so if those distinctions are really out there, then it hints that there is a deeper theory than quantum mechanics, a theory in which the mathematical structures are modal. So modality refers to exactly this kind of distinction between possibilities and actualities. The current quantum formalism is based on mathematics that is not modal, that is non-modal. So the only distinctions you have are between basically propositions that are true and propositions that are false. But you can also, there are other, for example, logic systems where you can have propositions that are possibly true or necessarily true. And these are distinctions that early 21st century mathematics cannot capture. It just doesn't have enough expressive power. So if these distinctions exist, then it at least hints at the possibility that there is a deeper theory in which suddenly these kinds of distinctions become inherent in the mathematical structures themselves. So you don't have to introduce them at the level of the physics postulates like I did. So in that sense, if this is really the right path to go, what I'm doing is I'm putting a very superficial veneer over frameworks that can't really handle it until the deeper mathematical structures are found. Obviously, more work needs to be done to work out the details of actualization and deactualization. That's probably the biggest setback. I simply represented state reduction in terms of a composition of 2 maps and didn't really explain what's going on. And I realized this is something that needs to be elucidated further. And again, it sets the stage for a novel prediction under the simplest possible assumption one could make about how gravity relates to quantum mechanics, and it suggests a big physics experiment that, in my opinion, would be one of the best big fundamental physics experiments we could do, because either way, it would be a success. Thank you for listening, and if you have any questions, feel free to email me at my email, which is my first name, armin@umich.edu, and I wish you a great day. Thank you.